Hello, everybody. Today we're going to finish up Chapter 6 on covalent bonding. We're going to talk about the three-dimensional shapes of molecules in section 6.3. The objectives is to predict the shape of a molecule using VSEPR theory. VSEPR stands for valence shell electron pair repulsion, or VSEPR theory. I like to call it VSEPR. Then we're going to associate the polarity of molecules with the shapes of the molecules and relate that polarity and shape of the molecule to the properties of the substance. I think I'm going to get rid of my face, give us a little more room. There we go. Okay, so here's the idea. What you're looking at are the Lewis structures of two molecules we're very familiar with. On the right, we have sucrose. Sucrose is common table sugar. On the left, we have a copy of table sugar called sucralose. And if you look at the two structures, they're very similar. But notice the sucralose, it has a slight change. Instead of hydrogens in certain places, it has chlorine. There's another one there and another one there. So the way this works is when sucrose hits your tongue, it's just the right shape so that the nerve cells, the taste cells in your tongue, recognizes it and sends a signal to the brain, and then the brain makes it taste sweet, gives you this sweet sensation. Now, sucralose is the same shape except for a few different atoms, these chlorine atoms. So it fools your tongue into believing that it's sugar, and then it fools the brain, which gives you a sweet taste. But the sucralose cannot be processed by the body like sugar can. The sucralose, it just goes right through the body. It's like you're eating a little tiny piece of plastic that it still gives you this sweet taste. The sucrose, on the other hand, it is processed by the body and it has calories. It gives you energy. So for people that are on a low sugar, a low calorie diet, they might want to use sucralose. And if you go to the coffee shop, you'll see the sucralose in these yellow packages. So here's the idea. If you only have two atoms connected in a molecule, connected covalently, you have to have a linear bond. It has to be straight, right? Two dots. What's the definition of a line? 2 points make a line, and it's linear. Here's another example, sulfur dioxide. It's got a sulfur in the middle, and then it has two oxygens. That's bent. If you look at it, the two oxygens are at an angle compared to the sulfur, and you can determine this angle using geometry. You can determine that angle. And I'm going to guess roughly it's 109 degrees. Here's another example, carbon dioxide, but it is linear. Notice that it's linear. Now, what is it about carbon with two oxygens compared to sulfur with two oxygens that makes the carbon dioxide linear? Why is carbon dioxide linear, but sulfur dioxide bent? Here's another example, boron trifluoride. Boron trifluoride, notice that it's got the boron in the center and the fluorines are stuck on the outside in a triangle arrangement. So we have the boron in the center and then the fluorines out here. And notice that the arrangement is the fluorines are all 120 degrees apart. And if you add up 120, you get 360, the number of degrees in a circle. So what is it about boron trifluoride that makes it this triangle shape? And it's flat. Notice also that it's flat. The fluorines, exist in the same plane as every other one. Here's another example, carbon tetrahydride. This is common methane, carbon tetrahydride. Notice how the carbon's in the center, and then each of the hydrogen atoms, they are spaced equal distance apart from each other. Here's another one, tin dichloride. Tin dichloride is a bent shape. One way to think about this, and that's the idea behind VSEPR theory, valence shell electron pair repulsion, is that these bonds between these covalent bonds between the central atom and the outer atoms, these bonds, they're made up of electrons. And of course, electrons have a negative charge, so they don't like to be next to each other. In fact, they will try to get as far apart as possible if they can. They will try to get as far apart as possible, and the most stable arrangement will have them as far apart as possible, depending on the magnetic charge and how many there are. That's the idea behind valence shell electron pair, and the key word is repulsion. The electron pairs, the bonding electrons, try to repulse each other to find an arrangement where they're as far apart as they possibly can be. Here's another idea behind this VSEPR theory. So here we have carbon dioxide, and it is a linear molecule. It's carbon in the Lewis diagram has carbon in the center. There's a double bond on one side, a double bond on the other side with the two oxygens. Now, the most stable arrangement of this molecule is a linear arrangement where the two oxygens are on opposite sides. So if you measured this angle, it would be 180 degrees. Now, it turns out that carbon dioxide, the carbon has a lower electronegativity than the two oxygens. So what does that do? It causes the molecular bonds, the covalent bond, to be closer. These two electrons, these two bonding electrons, are closer to the oxygen on that side, and the same thing happens on the other side. So that causes the center atom to be slightly net positive, the carbon is slightly positive, and the two oxygens on the ends are slightly negative. But it turns out that the pull on these electrons are opposite, are equal and opposite. For water, on the other hand, water, the oxygens or the hydrogens on either side, they're at an angle, so they're not pulling directly opposite to each other. The end result is that the end that has the hydrogens is slightly positive, and the end that has the oxygen is slightly negative. So water is actually like a little tiny magnet. If you get a water molecule, you have the hydrogens, and this is slightly positive on this end, and then where we have the oxygen is slightly negative. And so another water molecule will be attracted. This slightly positive of this hydrogen will be attracted to that one. And so we can create these big structures of water molecules. There's another hydrogen, so we got another. And basically we get a structure something like this. Okay, so how do we use the VSEPR theory? Well, it's all in a table, and here it is. So once you figure out the Lewis structure and you can count the places where the electrons are found, based on the places where the electrons are found, you can determine the shape. So all you do essentially is you determine the Lewis structure, you count the places where the electrons are found around the central atom, and based on that, you can determine the molecular geometry. Is it linear? Is it trigonal planar? Is it bent? And so on. Okay, so we're going to end it here, and the next step will be to go into the unit packet, and we're going to start doing problems. See you next time.